Okay, we're going to talk about angular momentum here. And here's how we're going to approach this. I'm going to show you, I'm just going to give you the definition of the angular momentum of a particle relative to a fixed point. And then we're going to follow that trail, see where it leads us. And when it leads us to the result that we would like to see in the end, then we will say, yes, that's where we should have started. So it's a little bit of a kind of a backwards approach to doing things, but I think once you see where the story ends up, you will understand why I'm just starting. I don't usually like to start just by dropping a definition on you, but that's what I'm going to do today, right now. So the angular momentum of a particle now, of course, a particle, just like moving through two-dimensional space or three-dimensional space, you might say, well, doesn't it just have regular momentum, like mv, mass times velocity? Yes, but we want to be able to talk about its angular momentum, and to do that, it might not be like an object that's like rotating on an axis, but we can still talk about its angular momentum relative to some point. So that's where we start, of a particle relative to a point, and we symbolize this angular momentum with a lowercase l, which I suggest you do a cursive L because otherwise it just looks like a stick, which could be confused for other things. And that is equal to R cross, this is a vector cross product, V. Gee, I don't know how to do a cross product, or that sounds vaguely familiar. So how am I supposed to do that? And sorry, I forgot to multiply. This is R cross V times the mass. And usually we put the mass first. I'm going to squeeze that in right here. So mass times R cross V. And what you need to know here is this. When you take the cross product of two vectors, what you get is another vector that points in out of the plane that these two vectors lie in. I'll come back and show you an example in a second. And how do you get the actual magnitude of this? Just like a dot product is magnitude of one vector times the magnitude of another vector times the cosine of the angle between them, a cross product is equal to, so let me scratch that. So the magnitude of L is R M V sine theta. And I always write it in this order, this R M V sine theta, but you can see this is the same thing, that the way we found the magnitude of the R cross V is by doing R times V times the sine of the angle in between them. So excuse me, this is very important. And just like with torque, this is very often going to be 90 degrees, but not always. The direction of it, it's not super important for us to dwell too much on that, except to say that we need to know like when two angular momentums are in the opposite direction as each other. So here, let me just sketch out a quick example for you. Here's an example of a particle with mass m and velocity v, and here is a fixed point. We often think of this fixed point as being like an axis, but it doesn't need to be. And here is the vector r that points from that fixed point to the location of that particle. And so how do you find the angular momentum of this particle relative to this fixed point? You might be asking yourself, why would you want to do that? Why wouldn't you just talk about its momentum, mv? Well, you'll see. We'll get there. But let's say you have committed to doing it. So how do you do it? Well, you just have to do RMV sine theta, where theta is the angle between them. That's really the obtuse angle here. Like if you took the r vector and put it here, like r and v were the two hands of a clock. But the nice thing for us is that the theta, I'm going to just put theta there because the sine of an angle and the sine of the supplement of that angle are the same number. So it does not matter which angle between the two vectors you pick, you're going to be just fine. So whichever angle is easier for you to figure out. Now, the direction of this vector is going to be one of two choices. If the plane here of this two-dimensional motion is this paper, right, this piece of paper, it's going this way in this piece of paper, in the plane of the paper, then there are two possible directions that the cross product that r cross v could be in. The two possible directions are directly out of the page or directly into the page. The two possible directions perpendicular to this plane. So how do you figure out which it is, and then how do we even think about that? Well, you think about it like this. The direction of r cross v, we use a version of what is called the right-hand rule. And we sweep. Now here it's useful to think of the where r and v are the hands of a clock. You do have to get the direction right. You do have to make that move. So you're going to take your right hand. Make sure it's your right hand. Right? If you're left-handed, sorry, it's a right-handed world, as you probably know, I'm sure. So got to use your right hand. Take your right hand, and since we're doing r cross v, you start by pointing your fingers, these are your fingers, pointing your fingers in the direction of the r vector. Okay? Now, we need to be able to sweep, which I mean go like this, to the v vector in less than 180 degrees. And to do that, you're either going to have your hand in this orientation. Can I get to R? Can I get to pointing from R in the direction of R to V this way by like closing my hand in less than 180 degrees? That's like going this way. No. So to do it, I have to turn my hand upside down, and now I can do that. I can kind of curl around from the direction of R to the direction of V. What direction is my thumb pointing? It's pointing directly into the page. Now, you notice that there's only two possibilities for what could happen here. So we can use the convention that usually into the page is usually what we consider to be the negative direction. And then out of the page is the positive direction. Now, it just doesn't matter which you choose. Like all the time when we decide, oh, let's make up positive. You can make up negative as long as you're consistent. So the thing that's important is that you recognize when two different particles, if we're looking at like total momentum, when two different particles have opposite signs for their angular momentum. That is the really important thing here. So this is how we do it. I'm going to, I think when I go through and do the homework problems, for the most part, I'm going to use this convention, that if I have to go like R, if I have to do that upside down, flip my hand over, and it's into the page, I'll consider that to be the negative direction. Okay, so that is how we do that. So the angular momentum of a particle relative to a fixed point is RmV sine theta. All right, and that's how we figure out the direction. Now, what if we have an object rotating, not a particle, an object rotating on a fixed axis? So let's start out with our lumpy kind of object. The axis definitely does not need to be at the center of mass, so I'll put it over here. That's the axis. And what is the angular momentum of this thing? Well, the angular momentum of this, which we will call capital L, for, it's not a particle, it's like a collection of particles. Angular momentum L is equal to the sum of all of the RmV sine thetas if we chop it up into millions of little tiny pieces. It doesn't have to be millions. Well, actually, it does have to be millions and beyond if you want it to be exact, right? As we would want to find the limit as the number of particles approaches infinity. We're not actually going to have to do any calculus here, but that's the idea. So if we added up the angular momenta of all these particles, what would we get? Well, let's take a hypothetical one of them here. We can add that into our drawing. So that would be R sub I, and this would be that little chunk. We'll call that M sub I. So what does this turn into? Well, how fast is this thing going? This is where, if this thing is rotating with angular momentum, with angular velocity omega, then here the angular velocity, the speed of this is the v is omega times r sub I, right? And that's the same, so that's that useful fact again here. So what does that turn this into? Then, oh, and what's the angle? For every single one of these particles, for every single bit here, the angle, since it's going to be rotating this way, it's always tangent to the path. Since we have this kind of fixed rotation, every particle is going to be going perpendicular to its radius. So the sine of theta for all of the bits. So what does this clean up into? So that's the sum over all of the particles that we've chopped it up into. R, M, V is omega times R1, so R, M of that particle, and then the V is omega R sub I, and the sine of theta, I'll just put it in this step, it's sine of 90 degrees, so that's going to be 1, that's going to go away. So rearranging this, we have omega is the same for all these, so as I sum over all of these m's and r's, the omega is the same for all those, so I could just factor that out. So I get the sum of all of the mr squareds, m sub I, r sub I squared, and times omega. And of course this, what's the sum of all the mr squareds for all the particles? That's rotational inertia, or moment of inertia. And this right here, that's the punchline. That is why we defined the angular momentum of a particle to be this. We defined it to be this so that it would lead us to here. And why did we want to get to here? Because this is just like, what is this? This is angular momentum. So that's like regular momentum, P, is equal to, what's this? Well, that's the rotational analog of mass. And what's this? That's the rotational analog of velocity. So we have angular momentum is equal to angular mass times angular velocity. I said angular mass here. That's not what we usually call it, but you get the idea. So angular momentum, angular mass, angular velocity, just like momentum equals mass times velocity. Yay! So that's good. That's where we wanted to end up. Besides just calculating angular momentum, you might suspect that in a collision where both objects, one of the objects could be a particle, that's possible, talk about an example of that in a minute, in a collision where both objects can rotate, they're both free to rotate, angular momentum is conserved. No big surprise there, right? Because in a collision where both objects are free to move, then linear momentum is conserved. Linear momentum is now, just like we talk about translational kinetic energy and rotational kinetic energy, now we have to just make sure we know what kind of momentum we're talking about. Are we talking about linear momentum, which is like the mv, or are we talking about angular momentum, which has two different forms? It could be that rmv sine theta if we're talking about a particle, or it could be I omega if we're talking about an object that's rotating on a fixed axis. Okay, so here's an example. This is one of my favorites. So we have a kid of mass m. The kid is running with a speed of v toward a merry-go-round. This is the overhead view, right? Kid's running here, and kid's going to jump onto the edge of the merry-go-round. And the merry-go-round has a mass of m and a radius r, and we're going to assume that it's a uniform disk, so its rotational inertia will be 1/2 mr squared. And the initial angular velocity of the merry-go-round is 0. But this kid's going to come running up and jump on the edge of this, and then it's going to start to rotate, right? That should make sense to you that that's going to happen. So how fast will it rotate? What will the angular velocity of it be? Okay, let's see if we can figure that out. So angular momentum initial is going to equal angular momentum final. Now, if you think about the initial situation here, it's just this kid running here. Now, this kid is not an object rotating on a fixed axis, so we need to treat this kid like a particle that has angular momentum relative to this fixed axis, So how do we do that? Well, you're going to see a couple problems, and there's a good example in the book on page 287 that the angular momentum of this kid relative to this fixed particle as the kid runs this way, it's constant because the r sine theta, the theta is constantly changing, but the r sine theta is not changing. So we just need to imagine when the kid gets right to here, what is the angular momentum of that kid? So let me just write that down. So that's the angular momentum of the kid, initial, is equal to, now what about final? Final, we have angular momentum of this thing with a kid on it, right? And that is capital L. So I want you to note right here that these two different kinds or forms, I guess would be a better word to use, of angular momentum can be equal to each other and will be equal to each other. And they have the same units. They have to, of course. So that's what we have here. We have particle, and then particle is attaching itself to fixed rotating object. So let's see if we can fill in the details here. So for the kid, we've got RMV sine theta. So the R, we're thinking about when the kid's right there, right when the kid jumps on, right? So R and then M of the kid, and then V of the kid, and then sine theta, but when the kid gets to right here, the kid's velocity is this way, the R is this way, so the theta is 90 degrees, and that's equal to 1, of course. Right? And here, when the kid jumps on, I have I total times omega, because that I omega is the angular momentum of a body rotating on a fixed axis. Oh, I kind of twisted the wrong way. This would be going this way, right? Okay, so what's that equal to? Well, let's see, RMV on this side. So the I total, you just have to be careful here. Remember that rotational inertias, that's like rotational mass. And if you start piling things on top of a rotating object, like other rotating objects or whatever, this the total I, it's just like mass. You just add up all the stuff, just like you're piling mass on top of mass. So the I total is 1/2 mr squared for the disk, or the merry-go-round, plus the rotational inertia of the kid. Now, how are we going to do that? Well, the kid, relative to the merry-go-round, is basically like a particle. So the what's the rotational inertia of a particle? It's just mr squared. So m of the kid is r squared. And then, you know, depending on what you know, and and then omega. What you're trying to find here, we could solve for maybe omega or whatever. So I'm not going to do any further algebra with this. I'm just going to leave you with that. And then just real quick here, I don't know whether you want to include this in your notes or not, I just want to give you a quick demonstration here that the RMV, so here's the kid. As the kid runs along, I just want to show you that the RMV sine theta stays constant. So here's the R. That's like the R of the merry-go-round is here. So here's the kid here, here's the kid here, and then here's the kid when the kid jumps on. And I was claiming, I was just looking at this saying like, oh, RMV sine theta, the angle's 90 degrees, so that's all easy. But is it in fact true that the angular momentum of the kid is constant as the kid runs? Let's say the kid just ran right past the merry-go-round. Is the kid's angular momentum relative to that axis constant? Answer is yes. That's the R of the merry-go-round. Here, what's that? That would be the R when the kid's right here. Okay, and then what would the theta be? Well, the theta would be this. So this right here, R cross v would be RV sine theta, right? That's how I find the angular momentum here. RMV, or put the M there. But I want you to look at the R sine theta. What is R? This hypotenuse times the sine of theta, opposite. That's the opposite side. So the R sine theta is equal to R. And that means that when the kid's here, you're going to have RMV sine theta again, but the R sine theta is still going to be equal to R. So no matter where the kid is, as the kid runs straight past here, as long as the kid's velocity is not changing, then the angular momentum relative to that axis is always just RMV. Because the R sine theta for all those different R's is always going to be equal to that perpendicular radius R right there. So that's good to know. All right, so I think that's what you need to know. Just be careful when you're doing like the first couple problems in the book that you pay attention to that positive, negative. The way I think about that is I just think about like a clockwise, counterclockwise. So if you've got a fixed point here and you've got one particle here and another particle here, well, this might be traveling in a straight line, so you don't really necessarily think of it as being as going around this point. But if it was going around this point, clearly this one is going clockwise and this one is going counterclockwise. So these two have opposite signs. And it doesn't matter which one you make negative and which one you make positive, but you definitely need to make sure that they have opposite signs. Because if you're finding the total angular momentum of this system of particles about this point, these two are going to do some canceling out of each other. All right, that's all.